Imagine two identical resumes crossing the desk of a hiring manager. Same education, same experience. One gets the job, the other goes in the trash. Now replace the human manager with an automated algorithm. You'd expect a logical outcome, right? Instead, the machine instantly approves one and rejects the other, which leads to a surprisingly difficult question. If computers don't have personal prejudices, how exactly does a machine learn to be unfair? For a long time, we've treated algorithms as purely objective, mathematical black boxes. We assume that because they run on code and numbers, they are immune to human flaws. But artificial intelligence doesn't operate in a vacuum. It acts as a mirror, scanning millions of past human decisions, identifying the hidden patterns, and scaling them up to operate at lightning speed. Researchers generally break AI bias down into three distinct layers: systemic bias from our institutions, statistical and computational bias in the math, and human bias from the people interacting with the system. Because AI simply absorbs and amplifies these existing flaws, we can't just look at the final output. We have to trace the technology's entire life cycle to see exactly where the unfairness gets injected. The injection starts right here, in what engineers call the pre-design phase. Every machine learning model begins by swallowing massive amounts of historical data. If you're building a tool to predict healthcare needs or assess criminal risk, the data you feed it was generated by doctors, judges, and police officers over decades. Any systemic biases present in those past decisions, like undertreating minority patients or over-policing certain neighborhoods, are baked directly into the numbers. A common response from developers is to simply blind the AI. They delete protected attributes like race, gender, or age from the spreadsheet, assuming the machine can't discriminate if it doesn't know who it's looking at. But that ignores a mathematical reality called redundant encoding. A person's demographic profile is deeply entangled with their other data. Delete a label like race, and the algorithm connects remaining variables like zip code and income to silently reconstruct the profile you hid. A dataset built on an unequal history will inevitably teach an algorithm to recreate past prejudices. Hiding specific columns in a spreadsheet doesn't fix the underlying reality. That brings us to the design and development phase, where engineers try to solve this problem by mathematically programming fairness into the system. To do this, they have to choose a fairness metric, essentially a scoreboard. The first option is demographic parity. This metric asks a simple question: does the system approve equal percentages of different societal groups? If it approves 20% of men for a loan, it must approve 20% of women. But look at this visualization comparing two different metrics. The second chart, equalized odds, measures exact error rates across groups. Forcing it to perfectly balance destabilizes demographic parity. Now, calibration enters, checking if a risk score means the exact same real-world probability. When aligned, the first two completely fall apart. These three fairness definitions are mathematically incompatible. When populations have different underlying base rates, choosing to balance one specific equation guarantees that another will fail. Choosing a fairness metric is not a solvable math puzzle. It is a strict moral compromise, and the right choice depends entirely on the real-world context of where the tool is going to be used. Which leads to the final stage, the deployment phase, where the algorithm is released to interact with real people. This is where a cognitive flaw known as automation complacency kicks in. Humans have a strong tendency to blindly trust a machine's output over their own judgment, assuming the computer knows best. When users act on biased recommendations, like sending more police to a specific neighborhood because a screen told them to, they alter the real world. They make arrests that might not have happened otherwise, which generates brand new data. That new data feeds directly back into the algorithm. The machine confirms its original bias and updates its model, creating a self-feeding, accelerating loop. Left unchecked, these systems generate the very reality they were meant to predict, reinforcing past inequities into a permanent cycle. Mitigating AI bias demands continuous detection, requiring developers and researchers to track disparate impacts long after the code is finalized. This diagram illustrates a critical technique called intersectional review. Instead of analyzing error rates for minorities or women separately, we look at the center of the diagram to catch overlapping vulnerabilities, like the specific error rates for minority women. Real-world researchers like MIT's Joy Buolamwini used this exact intersectional approach to expose compounding failures in commercial facial recognition systems that were completely missing darker-skinned female faces. Managing this risk requires constant monitoring across all 3 stages of the loop: before the data is gathered, during the mathematical modeling, and after the tool is deployed. Building trustworthy AI demands systemic guardrails. We need transparent design processes, extensive documentation of model training, and clear paths to appeal decisions. Mathematical fairness is an illusion without human accountability, and artificial intelligence will only ever be as fair as the society